Good afternoon and welcome to today's electronic design webcast. Our topic today, properly scoping TSN, Ethercat, and Opc Ua is the key to protecting your machine controller's future. Sponsored by Interval Zero. I'm Bill Wong, Senior Content Director with Endeavor's Design and Engineering Group. To begin, let me explain how you can participate in today's presentation. First of all, if you have any technical difficulties during today's session, simply type your issue into the Ask a Question box and a member of our team will assist you. You can also click on the question mark Help button in the upper right corner of the screen. Additionally, we welcome your questions during today's event. We'll answer as many questions as possible during the Q&A session that will follow the main presentation. But please feel free to send in your questions at any time. To do so, simply type your questions into the Ask a Question box and click on the Send button. If you would like a copy of the presentation, please click on the event resources on the side of your screen to download the presentation. Also, please be aware that today's session is being recorded and will be available on the Electronic Design website within the next week. You'll be notified by email when the archive is available. Now, let's meet today's speaker. The driving force behind the formation of Interval Zero in 2008 is Jeff Hilberg, CEO of Interval Zero, who led the acquisition of the RTX-based RTOS embedded technology. Delivering his 20 years of experience in software engineering, sales, and marketing, Jeff has since guided Interval Zero to become a marketing leader in supplying RTOS technology and machine automation software to world-class organizations in industrial automation, surface mount technology, test and measurement, semiconductor, healthcare equipment, aerospace and defense, and many more industries with deterministic requirements. Now let me turn things over to our presenter. Jeff, the floor is yours.
Thank you very much, Bill, and thank you everybody for attending today's webinar. My hope is to share how TSN, Ethercat, and Opc Ua, which are new technologies, can be applied to ensure your machine controller will be able to continually adapt to all the rapidly changing markets, demands in the market. And just to give a little context on what I am trying to share today is that recently, many of our best customers have asked, should I re-architect my machine controller to replace my fieldbus, which is most of the time Ethercat, and replace it with Opc Ua or TSN? And if not, how should I implement these technologies? So given that so many people are asking these questions, because there's a lot of confusion in the market about driven by marketing from big corporate manufacturers, I thought I would just give a summary of what we're seeing and explain why what the appropriate implementation should be. So at the end of this presentation, my hope is that you'll see and understand why customers are asking these questions. You'll understand the best way to implement Ethercat, the best way to implement Opc Ua and TSN, and also understand why there's so many new deterministic or hard real-time requirements emerging in or why the demand is increasing and why these standards are evolving. The agenda that I have in mind to make this happen is that first, we have to understand the context of our market. What are the four major market trends that are driving new networking requirements for machine controllers? And then I'm going to talk about these three technologies and why they emerged to meet these requirements. And then what we'll do is we'll look at three different architectures for how you can implement these technologies to satisfy the need. And then we'll kind of rate them to understand what the trade-offs were between implementing each of these different technologies. And then finally, I'm going to give you a vision for where the market is going and why, if you implement these technologies properly, you'll be protected into the future. And of course, as Bill said, we'll have a quick Q&A at the end. So first, I'm going to start out with the four trends that drive controller requirements. There's new fieldbus standardization, machine consolidation. A lot of people are hearing about IoT, what's the role of that, and then IT-OT convergence. And I'm just going to touch on these from the perspective of what is the network requirements to result from them. So with respect to fieldbus standardization, standards that get adopted benefit the consumer and the customer greatly. Okay, just think of the PC. In the beginning, if you had a custom PC and you only had, everybody had a custom PC, then all of a sudden switching costs are high. But as the PC became standard, all of a sudden people could swap out and protect themselves. And this drives the cost down. At the same time, the quality of the product goes way up and the innovation goes way up because the more competition in the market, the better off it is. And also you avoid vendor lock-in, where vendors that do lock you into a proprietary environment prevent you from, get to charge a premium for that. And the same can be said for field buses. There's a lot of field buses that are emerging over the last decade, really, that standardize on Ethernet hardware. But the best standards are the ones that actually get adopted. And what you're going to see is that through the standardization effort, what customers are asking and the networking requirement that precipitates from the standardization is that the network must deliver determinism for every controller inside the machine, and it must optimize the way that information gets shared with all the IOs and servo drives that drive a machine. The controller also has to be able to work with other controllers and communicate, because we're seeing more and more times machines need to communicate amongst machines. And then finally, a given controller, even inside the controller, is going to require multiple deterministic protocols. So for instance, there's a new trend called vision-directed motion. There's a protocol, Ethercat, that does the driving of the motion elements, and there's a protocol that's real-time that collects the image called GigE Vision. So with respect to the standards, I'm just going to make a quick comment about which standard we think is the best. There are 5 major Ethernet-based standards. 3 of them, Profinet, Surcos, and Ethercat, really have very similar performance profiles. But the one that really stands out is Ethercat. And the reason that is that so many vendors in the supply chain have adopted that as a standard. And so remember, if the standard gets adopted, then there's more competition, switching costs are lower, and now you can switch out one server drive for another server drive, one IO for another IO, and it doesn't really matter. And what that does is the vendors have to have better quality and lower price in order for you to achieve the best success for their solution. And so it's only the standards that get adopted really drive the best optimal determinism and have the best cost performance profiles. So while Profinet is an outstanding protocol, and so is Surcos, they've just not been adopted outside the local major manufacturer provider. The next major trend is machine consolidation. This is happening especially in the semiconductor industry, where there used to be several islands of automation. And now these islands of automation are being integrated as a single machine. So there's a lot more going on. And there's a great study done by Deloitte that really focused on, if you're able to integrate, rather than just optimizing one machine, but if you could optimize the work cell together or optimize the factory, which means you optimize the individual performing machine controller, and then you optimize the interaction between controllers, there's an exponential value you get from being able to get them all to work together. So this consolidation effort is resulting in new network requirements that says multiple machines must work together as a single machine. It must be viewed. And if you can achieve that, then you get these exponential results. Also, in order for you to do that, an upstream machine controller needs to share information in a variable format to downstream processes so that the downstream process can learn from the upstream. And that's where you start to get the value of this integration. Also, in a work cell setting, you don't want the whole cell to go down if one operation or one machine goes down. That the other ones can continue running until the other one comes back online. And there's lots of reasons you want to do that, even inside a machine where I want to take down part of my machine to do an upgrade of the software inside the machine while the rest of the machine continues running. And there's scenarios, especially in the semiconductor industry, that's driving that. 2 architectural options do emerge. One is you could keep all these machines standalone and then just build better integration between them, or we've seen a lot of people moving many controllers to a single PC. The third trend that we see in the market that's driving requirements for your controller that have to do with networking is IoT. So IoT, fundamentally at the most fundamental level, all it's trying to do is share this information from a individual machine for a work cell or from the enterprise up to an analytics or AI kind of environment. And then it generates an actionable insight, okay? And so when that insight comes back, you want your environment, your ecosystem to be able to take advantage of that new information and automatically moderate. You might have two work cells that are exactly operating perfectly, but then one starts to drift out of compliance. You want to detect that that's happening so you can send instructions back to get the first machine or work cell back in compliance. And what we're finding is an architecture that's emerging for this is that all software solutions, there's even a major vendor that's always sold proprietary hardware, non-PC based. They use FPGAs and ASICs to drive their hardware. They're now saying, you know what, we're going to go to a PC with software. I can't tell you who they are, but it's very exciting. The industrial PC also protects the future of your IP because you have a lot of third-party software. So rather than being on a proprietary controller, you could run on a PC, you get access to AI software, you get access to networking software. So you don't have to recreate all that software yourself. The fourth and probably one of the most complex issues facing machine controllers today is the IT-OT convergence. So IT is, of course, runs your information systems inside the company, and the OT are the operational and process events that happen on the shop floor. But because of all this convergence that we're talking about, where you're having consolidating multiple operations, now all of a sudden your OT machine controller is connecting to the cloud, and it's also sharing information with other controllers. But then they're using the IT network to do that. Well, this is putting a huge burden on the IT department because there's security issues, there are network capacity issues, and sometimes different implementations could expose devices inside of machine control. So if you have a machine controller and then you have the IOs and the drives, sometimes a cyber attack could actually happen on your device. I'm not sure if people remember the Stuxnet where the centrifuges ran out of control and the cyber attack that upset the uranium mining. That was done. That was where a virus got past the firewall and got into the devices. So anyway, OT needs to comply with the IT standards and use this system, the network, judiciously but appropriately. And they want to avoid these security threats I just mentioned. So just netting it all out. So we looked at 4 trends. I'm only focused on the trends with respect to the network issues and the way you kind of categorize them. All the requirements we just heard were that there are intra-machine networking requirements. So you have to deliver determinism and you want to coordinate the devices. You want to make sure that you have the optimal, so you can optimize your internal machine. And Ethercat offers the strongest standard for doing intra-machine networking. And then you also want to have your controller be able to support multiple protocols, like we talked about GigiVision and motion control on the same backbone and the same PC. You also want to have secure communications to protect your devices from being attacked by an outside cyber attack. And then you also want to share and be able to respond to actionable information. Then there's the inter-machine networking requirements that have emerged from these 4 trends. And you want to support machine-to-machine deterministic communication. Let's just talk about quickly a load-unload operation to CNC. I have a load robot, an unload robot, and I'm loading a CNC. I want to make sure that there's no collision. I want to detect a collision. I want to avoid a collision by sharing that information. And the only way you can do that is through determinism. Also, if my load robot goes down, I don't want to shut down my whole cell of the CNC machining and then the unload robot. So you could have an operator step in and start feeding the CNC, and then the unload robot can take it out of the chuck and so on. So there are different use cases where you don't want the whole cell to go down just because one servo drive goes down. And that's where the inter-machine networking has different requirements than the intra-machine networking. Also, you want to be able to concurrently use the IT and OT network as one. And so we have to find a way to layer in multiple protocols on a single Ethernet cable. And you also want to be able to support large data transfers between these machines. Okay, so I've tried to summarize the trends, look at the market. Now I'm going to talk about what are the technologies that are available. And of course, there are Ethercat, Opc Ua, and Tsn Time-Sensitive Networking. Let's see where we are. So Ethercat basically is a paradigm that replaces a point-to-point communication with a slave-master model, and it uses a daisy chain to connect. So if you look at the picture on the upper right-hand corner, we kind of have a before and after picture of how Ethercat works. On the left is the old way, where you have a proprietary I/O controller, you have proprietary cables, and you talk to proprietary drives. And with Ethercat, what you do is use a TCP I/O rather than a proprietary I/O. And the TCP NIC card is the I/O. You use a TCP cable, and then you talk to the drives, connecting them with a TCP cable. The value of this is that you save 56% of the machine control cost by just going to Ethercat versus a machine controller that uses proprietary hardware. But the real upside is that you get the optimized, high-performing, highest quality machining and information sharing because it's optimized specifically for this kind of motion control application. So Ethercat is really targeted toward intra-machine deterministic computing. The next networking standard that has emerged is something called Opc Ua. And really what it is a platform that provides independence and ensures a seamless data flow between disparate machine controllers that everybody can talk to everybody. And it does it using a secure, encrypted, authenticated mechanism. And that interoperability allows you to start to have optimized the cell because you have upstream processes and downstream process machine controllers now that can talk and pass information so that the downstream process can benefit from the learning in the upstream process, or you can share data to the cloud, get the actionable information, and then, again, adjust your processes accordingly. The downside to Opc Ua is that it's not deterministic, which means you can't depend on it completing on time every time. And so you could put in Opc Ua to have an upstream process and downstream process, but what you have to do is slow down your machine enough to guarantee that you won't have any kind of collision or that the process can finish in time before the next process starts. So really, Opc Ua was targeted toward machine-to-machine communication, the SCADA to machine-to-cloud communication, and so on. So now let me introduce the next networking technology, which is really gaining a lot of steam right now, and that's TSN, Time-Sensitive Networking. And really what time-sensitive networking says is it recognized the requirement about IT-OT integration. And what it seeks to do is converge multiple protocols over a single TCP cable. So you can, using a new traffic shaping and scheduling quality of service standards that are all IEEE standards, time synchronization standards, they apply all those in a way. It's not a protocol. It's not like TCP where you can plug in and have it go. It's not. It's a standard, and that standard can be applied to make integration. But what it really can do, and the upside benefit, is that it can add determinism to a normal protocol. So, for instance, right now, Mitsubishi has something called CC-Link IE, and they need a chip on the board to give the determinism on that protocol. Well, now you can move that to software, wrap it up in TSN, and all of a sudden, Mitsubishi can get rid of the proprietary chip and just run it as software on a PC, and it can be deterministic. So that's the value of time-sensitive networking. And really, all it is a protocol that allows you to prioritize, or it's a standard that allows you to standardize multiple Ethernet protocols and have them run on a single platform. So this brings us to the question, okay? The beautiful thing about Opc Ua over TSN is that it's like the Reese's peanut butter cup, right? You have the chocolate, you have the peanut butter, and they kind of run into each other, and next thing you know, bam, it really is great. Opc Ua is this fantastic communication for seamlessly transferring important and variable data between devices, but it's not deterministic. And TSN is a protocol that can help transform Opc Ua into, or is a standard that can help you transform Opc Ua into a deterministic protocol. And so what that means is that now you can use Opc Ua with TSN as a communication layer between two machines. And then what that does then is it allows you to speed up your environment, optimize your environment for the machine-to-machine communication. So it's highly valuable. But this leads to the question, should I re-architect my machine? This Opc Ua TSN is so powerful on the machine-to-machine communication. Why don't I go TSN all the time? Why don't I just go talk to my drives as well? I can get rid of my field buses, or I could have a different kind of controller. I could make sure each of those servo drives all talk to TSN. And the answer is, can you do it? Well, it depends is the first part of the answer. And the second one is it's absolutely possible, but it's rarely recommended. I'm going to talk about the scenarios now by giving you an example of the three architectures for how you might implement them. And the best way for me to do that is to give you a customer example that we're working with right now, so you can understand how they're thinking about some of the problems. Let's say I have a PCB, the green printed circuit board lithography controller. It's got 6 motors on it. And then I have a loading robot, 6-axis loading robot, and a 6-axis unloading robot. And there's no network here yet. And I want to do collision avoidance. So I want to make sure I detect the load and the unload as they feed this lithography machine. I want to make sure that I don't run the circuit boards into them. I want to make sure my unload puts the board successfully on the conveyor for downstream processes. So what network standards could we apply from the 3 that we just talked about, and how would we apply them here? Well, the first model is we could go to an all TSN model. And in this model, if you look at it, the TSN in the middle of this picture, the TSN switch in the middle of this picture controls the load robot, the unload robot, and the lithography machine. And this is a perfect use of TSN because remember, the requirement was if one of my devices on the TSN network goes down, could my rest of my ecosystem continue running? So if the load robot goes down, TSN could still have the lithography machine and the unload robot work, and just put an operator to load the machine. Conversely, if you look at within the machine, the unload robot, I have 6 motors there. If one of the drives goes down, does it make sense? Could my load robot continue to work? And the answer is no. So putting a TSN switch inside the machine is overkill, because even if one of the real value from having TSN and Opc Ua is that if one node goes down, the rest of the ecosystem can run. But if you're using it inside the machine, then you lose the real benefit. And all you're doing is adding, look at all this networking that you're adding. It's a huge amount of networking. You have to add a lot more switches. The costs start to go up. And by the way, TSN is not a protocol. So you have to do all that integration work. So if it were the case that one of the motors could go down and your machine continues running, then yes, TSN might be a really good answer for you. But if it's the case that inside, one of the motors goes down and the rest of your machine can't continue running, then it doesn't make sense to add TSN. The next approach would be more or less a all Ethercat approach. So in this model, you can see that we have the lithography machine runs with a single daisy chain cable, and same with the load and unload robot. Looking at the unload robot, if one servo drive goes down, then the other 5 servo drives inside that unload goes down. But the fact of the matter is, I can't run a 6-axis robot unless all 6 axes are working. The Ethercat master, however, can now talk to the load and unload. The external master can talk to the load and unload, and it works just fine. If the load goes down, however, then the unload also goes down. So this is where you kind of have to ask yourself, well, if I lose one servo drive in my load master, basically my whole cell goes down. And do I want to lose do I want to lose the whole cell? So this is where there's this trade-off that you have to think about with TSN versus Ethercat. I just would like to say, even though I said all Ethercat, we have lots of customers that actually use Profinet under the covers, but could use an Ethercat front end for the communication. So you can use any drive bus underneath the covers to drive the 6 motors. And I just want to make sure that when I say all Ethercat, I'm talking more about the way everything interacts. So let's talk about the hybrid approach. This is kind of the model that we recommend, because this fits the model the best. If you look at the actual machine, intra-machine, you want to have an optimized, highest quality, highest performance model where you can have all 6 systems work. If one of the drives goes down, the whole system's gonna be down anyway. So no need to overkill with all the TSN. And you'll notice that it's a very simple wiring. It's just a TCP cable to a TCP cable, on. And the TSN switch gives you fantastic control to take down a major system as you go. So just to kind of net it out then, here were the requirements that we summarized at the front end of the presentation. And you can see that, there's some places Ethercat really shines. It's the inter-machine communication, the plug and play of the machine devices is totally available. You can take out one drive, like a Copley drive, and put in a Yaskawa drive. Works like, just reboot the system and all works. Where you can see Ethercat is weak is that you don't want to use it as often unless your whole work cell goes down. You only want to use it in an offline mode. And that's why this hybrid mode turns out to be the best. So now I'm just going to make one comment about the future of the controller. Why is this so important? What we're hearing from our customers now, the tools that we've been working with are more locally centered. And what they're asking us is to move the tools into the cloud. And it's not just remote management. They don't want to just have a lights out manufacturing where they can do maintenance on the software. What they want to do is in real time, not, in current time, I should say, not like hard real time. But the idea is that if I have an assembly line and I have a car coming down, and it's a 4-door car, I want to send the instructions for the welding robots to weld a 4-door car. And then if a 2-door car comes down next, I send the instructions for a 2-door car, and it does the welding properly. And all the robots and all the functions have to intersect with this cloud. And using this TSN switch as the vehicle that will deliver these images is going to protect the future of your controllers. So no longer can you be an island of automation when you think about your system. You really need to think about the ecosystem and how you're going to optimize the work cell and take us one step further to the factory. So one last comment before we go to the question and answer. I just want to share that, Interval Zero has been around since 2008, but its original incarnation was 1980. So we've been around a long time. We have a lot of experience with machine control. We have 2 products. One is RTX 64, which is basically a real-time operating system, or an RTOS. It uses Windows for its front end. So it's a really great user experience. And you can build your foundation from that. The Kingstar is, we had a lot of customers saying, well, gosh, I want Ethercat libraries. I want other field buses. I want motion control. I want a PLC. And I want to access your real-time vision product called Kingstar, or your real-time vision product. So we wrap that up all as a prepackaged product. So it's just want to say that if you're thinking about building your controller, there's 2 good platforms for how to do that. So with that, I'm just going to hand it back over to Bill to kind of tell you how the Q&A can work from here. But thank you for your time so far.
Great. A few of you have already submitted questions, so we're going to jump right in. If you'd like to submit a question, type your question into the Ask a Question box and hit the send button. Also, please take a moment to complete the feedback form, which will appear on your screen at the end of the webinar. So to start with, how does safety impact the way you implement Opc Ua and Ethercat?
All right, so that's an excellent question. I'm going to see if I can go back to my slide for Ethercat first. Where'd I go? So, normally what happens in a safety scenario, you have to have a second network to allow for the safety to occur, right? You have your main, all the on the upper right-hand corner of this picture, you'll see that you have this home run cables. And then if there's a safety stop, you need to have a separate network to take care of that. And then with respect to Ethercat, the safety fail-safe, it's called FSOE, but fail-safe over Ethercat allows you to plug right onto the same main backbone. So while there is some work to do, and you have to write your applications to be able to do the immediate stop and safety requirements, that is, it's all, the architecture's all there, the hardware's all there. It's just a matter of making your applications ready. With respect to Opc Ua, it's impossible to use Opc Ua by itself without safety because it's not deterministic. In order for you to have safety, you have to have instant stop. And so adding in the TSN that becomes a good solution. However, the integration for that then becomes a real problem because you have to create a whole nother safety mechanism, takes more integration and more switches and so on.
You mentioned RPC, or remote procedure call. Can you give me an example for that context?
Yes. So the variable data, the remote procedure calls and so on, the way that works is in these integrations, when you're looking to build this kind of hybrid environment, you want to share information downstream to another machine. So you have an upstream machine, you have a downstream machine, and you want to share information. Let's say you're controlling a robot. There might be situations where you do all of the calculations to figure out what command you need to send to the robot. So this is a way for you to interface with a robot that has its own controller that doesn't fit into these kind of network models. And if you use TSN to send the message or other variable data to that downstream, and the best way to do that is through a remote procedure call.
You said that TSN is used in the machine controller context, but where else can it be applied?
Okay, so yeah, we're machine automation heads, but it turns out that TSN is, again, a collection of standards, and what those standards do is they prioritize many protocols. So actually, TSN right now is being used in a lot of automotive applications. You've seen maybe that there are a lot of shortages of chips and that kind of stuff, and the reason, and so cars are not being able to be made, and the reason that is that your car is kind of like a rolling computer, and so TSN is being used as the network inside. And what you want to do is be able to have a quality of service, so different readings and different messages on that same Ethercat backbone can be delivered. It's funny, the TSN standard was developed originally out of the music industry. Music mixing board companies wanted to have a way to plug in guitars and microphones and digitize all that, and then give a way to prioritize what things get together. So music industry, office, there's many different applications.
Well, I'm afraid we've run out of time. For those questions we didn't get time to answer, we'll be getting back via email. That concludes today's presentation. On behalf of Electronic Design, I'd like to thank Intel for sponsoring today's event, and of course, to all of you for joining us. Have a great rest of the day.